In this series of videos, we will review some of the key concepts from Calculus 1 that are necessary to be as successful as possible in Calculus 2. The first topic of interest is limits. So recall from Calculus 1, we say that the limit of a function as x approaches a is equal to some number L if we can make the values of f of x close to L by making the inputs close to a. Now recall when we're making the inputs close to a, they can be on either side of a, but they cannot be equal to a. Let's look at a motivating example. Just as kind of a reminder type problem, let's determine the limit as x approaches 1 of this function. Now, the thought process here is to remember that you want to think about plugging this number 1 in. But if we plug 1 into the bottom, the function becomes 0 in the denominator, which is undefined. So instead, maybe we can think about this from an algebraic perspective. We hopefully immediately see that the x squared minus 1 in the numerator is a difference of squares. So we can write that as x plus 1 over x minus 1 divided by x minus 1. Now the x minus 1 in the top and the bottom cancel, and what we are left with is simply the limit as x approaches 1 of the function x plus 1. So going back to this idea of a limit, by making x close to 1, what is x plus 1 close to? Well, if x is close to 1, 1 plus 1 should be close to 2, which is the value of this limit. From a graphical perspective, our function x squared minus 1 over x minus 1 is equal to x plus 1 whenever we are not at 1. So essentially what the graph of this will look like is a line going through y-intercept 1, slope 1. But at 1, it is undefined. So from a graphical perspective, we're thinking if we plug in something close to 1, whether it's on the left or on the right, those function outputs should be getting closer to 2. Let's look at one more example from this kind of graphical perspective. So, to first evaluate the limit as x approaches 2 from the left, we're thinking if we plug in an input into our function a little bit smaller than 2, we trace up to our graph, and it looks like those function outputs are going to be close to 3. Similarly, if we investigate the limit as x approaches 2 from the right, if we put an input just a little bit to the right of 2 and we trace up to our curve, we see that those function outputs are going to be close to 1. So the limit as x approaches 2 from the left is 3. The limit as x approaches 2 from the right is 1. And if the limit from the left is not equal to the limit from the right, then we would say that the limit itself does not exist. So this is because the limit as x approaches 2 from the left is not equal to the limit as x approaches 2 from the right. Lastly, the limit as x approaches 3 of our function. If we plug in an input close to 3, whether it's on the left or on the right, we see that the outputs are going to be close to this point here, which is an output of 2. Let's now look at a more analytic example. So the reminder from Calculus 1 is we have these things called limit laws that tell us essentially that we can do what we would like to do as long as it makes sense. And when I say as long as it makes sense, what we're really getting at is we don't end up doing things like dividing by 0, because mathematically that would not make sense. So in this example, we're taking a limit as x approaches 4. So we think, is it okay to plug 4 into the bottom? And here it's okay. So what we would do is apply our limit laws. The limit laws tell us that we can take the limit of the top, divide it by the limit of the bottom. And in the top, we have a limit of a square root. And one of our limit laws tells us that we can take that limit and plug it underneath the square root. And additionally, since we are all limit experts, we've seen this stuff in the past, when we put that limit under the square root, we can also break it up over the sum and write it as the limit as x approaches 4 of x squared plus the limit as x approaches 4 of 9, all divided by the limit as x approaches 4 of x. And this is really the ideal situation because now all of the remaining limits work out extremely well. So in the top, as x approaches 4, we can simply think of taking that 4 and plugging it in. It becomes 4 squared. The limit of a constant is always that constant. And as x becomes close to 4, well, x becomes close to 4. So this becomes the square root of 25 divided by 4, which is 5/4. And now to finish it up with just a general property, something the textbook called the substitution property. If a function f is a polynomial or a rational function. And remember what a rational function is. A rational function would be something of the form, we'll say f of x equals p of x over q of x. So that would be a polynomial over a polynomial. And this is the ideal situation. Evaluating the limit, the reason we call it the substitution property is you simply plug in x equals c. And this is true as long as you are in the domain of the function. And now it turns out there's nothing special, extremely special, I should say, about being a polynomial or a rational function. The key thing to remember is that polynomials or rational functions are continuous. So essentially, we can restate this as the continuity property. If you have a function which is continuous at some input c, then in order to evaluate the limit, you simply plug in the value of c. And this really is nothing more than the definition of continuity at a point.